We're going to build on the example that I showed you last week for left-hand rule and right-hand rule calculations in Excel and improve the calculations going on to make more accurate numerical estimates of integrals with smaller numbers of partitions. The two techniques you're going to learn about here are the Trapezoid Rule and Simpson's Rule. They are both better than the left-hand rule or the right-hand rule. The Trapezoid Rule is a direct averaging of the left-hand rule and right-hand rule. And Simpson's Rule is a little bit more sophisticated, and you can read about all the whys and wherefores of how it arises in either of the texts that you have access to, either your own or the PDF text that I've made available. What you see on the screen here is from that PDF text, and it's a statement of Simpson's Rule. So in the notes for the class, you'll see kind of a comparison of the notation for left-hand rule, right-hand rule, and Simpson's Rule. What you're going to note is that we are doing a Riemann sum type of process. So if you ignore that divided by 3 on the front coefficient for a moment and ignore the 4, 2, 4, 2 business in the coefficients, you just have an f of x times delta x plus another f of x times delta x plus another f of x times delta x. So you really are just summing the heights times the widths of a bunch of rectangles like before, except now they're weighted by these coefficients, 4, 2, 4, 2, and so on. And there's also this other little division going on out front, which is sort of like a weighted average of the different components that go into this. So what we're going to do is look at how can we implement a formula like this into Excel. Now, I don't want to spoil your fun in figuring out how to implement the Trapezoid Rule or Simpson's Rule. So what I'm going to do is pretend that there is another numerical integration technique called Luther's Rule. And here's how Luther's Rule works. Okay, this doesn't really work, so never use it. It's just going to be an example. But let's suppose that for my numerical integration, what I need to do is take my interval of integration, chop it up into partitions. I have my list of endpoints of all those partitions, x1, x2, x3, all the way down the line from x equals a to x equals b. I have a delta x because of my partitioning, and then here's the formula that I'm going to put my f of x's into along with the delta x. Notice I've got a division by 4 out here in front, and I've got alternating coefficients of 3, 6, 3, 6 all the way down the line, except for the first and last coefficients are just 1. So again, pretending that this is an actual numerical integration calculation, I'm going to show you how I could implement it in Excel. Whoops, I see an error there, over there on that second to last term. So I'm going to fix my parentheses. This is called Latex. It's a mathematical typesetting markup language. It's like HTML for math, and it makes really slick-looking equations. Okay, so that's better. So what we're going to do is go back to Microsoft Excel and just pick up where we left off. So this is a calculation that we did last week where we are integrating the function e to the negative sine of x. And remember, that calculation is happening inside these cells in column F. So column C has my endpoints. I'm integrating from 0 to 5 with 12 partitions for the moment. So here's x equals 0 all the way down to x equals 5. And there's 12 hops, 1, 2, 3, all the way down to get from 0 to 5. The width of each partition based on going from 0 to 5 with 12 steps is 0.417-ish. At each of those endpoints x, I calculate my function f of x, which is e to the negative sine of x. And then for my left and right-hand rule, I just calculated f of x times delta x for all these f of x's, and then I would add up the appropriate ones. Like for my left-hand rule, oops, I got to back up one. For my left-hand rule, I would add up the results from all of the endpoints except the last one, because the last one was not a left-hand endpoint of any of the partitions. And then the right-hand rule omits the first one because it's not a right-hand endpoint of anything, but then gathers all the left. So let's say we're going to do the same function, or the same integral, 0 to 5 integral of e to the negative x sine of x, except this time we're going to use this totally made up and artificial Luther's method for doing a numerical integration. Okay, what am I going to do in Excel? Well, first of all, note that this delta x is really multiplying this f of x, this f of x, this f of x, and this f of x. So in my Excel spreadsheet, this column still has a whole bunch of good stuff in it. In fact, all I need to do is go to these values, which each go with one of these terms, and I need to figure out a way to multiply them each by 1 or 3 or 6, and then I also have to divide the whole kit and caboodle by 4 when it's all said and done. So that's actually relatively easy to fix. So here's Excel. Whoops. Here is Excel. In this next column here, column F, I'm going to enter coefficients. And these are the numbers that each of those terms are multiplied by. And remember the pattern was 1, 3, 6, 3, 6. Now, if you're making a long list, you may not want to copy it all the way down, so you can just take a chunk and recopy it, and recopy it like that. And remember that the last coefficient in the list is 1. I'm going to flash back here again. There's a whole bunch of endpoints, the first, second, third, fourth, all the way down to the last one. The first and the last one have a coefficient of 1, but then we have 3, 6, 3, 6. Well, the pattern alternated between 3 and 6, and I may have, in my made-up numerical integration, maybe that should have been 3, okay? Because if I just continue this pattern of 3, 6, 3, 6, 3, 6 all the way down, I end up with 6, 3, 1, which is nice symmetry going into the sequence 1, 3, 6, coming out of the sequence 6, 3, 1. So yeah, if I was making up a proper numerical integration, which again this isn't, this probably should have been a 3. And then just to confirm against a real numerical integration, notice here for Simpson's rule, you get 1, 4, 2, 4. So it starts with 1, 4, 2, and then has alternating, and then it ends up 2, 4, 1. So there's this nice symmetry from the left side to the right side of the terms with the 4s and the 2s, and then ending in 1. So continuing with the fake numerical integration technique, here's my list of coefficients. So what I'm going to do is I'm going to insert a new column. And in this new column, what I'm going to do is I'm going to take this f of x delta x, each of those, and multiply it by the coefficient. So I'm just going to call them terms. What the heck? So the first term would be this coefficient times this f of x delta x. And then I'm just going to copy that down. The referencing will update so that if I just pick a random one like right here, the cell in column G is the product of these entries of F and E to the left. So this would be, say, the term 6 times F of X, whatever, F of X 6, okay, because it's right there in the middle. So what I've done with this column, this new column G, is I've created all the terms in this summation, and this delta X is already included as a multiple of all of those, because remember in Excel, I'm creating f of x times delta x, f of x times delta x, and I've also put on the multiples of the coefficients. So I'm almost ready to calculate Luther's rule. Here, let me get rid of the left-hand rule. Here comes Luther's rule. Okay, what I'm going to do is I'm going to sum. I don't want to sum from column E anymore. I want to sum all of these. With the left and the right-hand rule, I had to leave out the first or the last. This time I don't want to, because they're all included. So what I've done, again, is I've now made this entire summation take place. The only thing I haven't done is do this division by 4. But that's easy. I'll just go here and take my big giant summation and divide it by 4. And there we go. My Luther's method estimate of the integral from 0 to 5 of e to the negative sine of x dx is about 5.6. Okay? This is totally wrong. I can't emphasize this enough. Do not use Luther's rule to do any integrals. I just didn't want to do Simpson's rule straight up, but if you kind of followed what was going on here in the way that I was taking a recipe that had a whole bunch of f of x times delta x's, and coefficients attached to each one of them, how I can lay out that calculation inside Microsoft Excel to give me a result. So again, you're going to take the results you had from last week and you're going to update a particular selection of the problems from last time and implement the Trapezoid Rule and the Simpson's Rule. And I hope this little overview helped.